since we're starting in the middle of Peter's last lecture, we're going to just leap into the AI news of the day. And we've got a couple interesting items. So the first one is, this should surprise no one. Lawyers are using ChatGPT or other AI systems to write briefs and all this stuff. And it should surprise no one, they're getting caught. In this particular case, this just happened, I guess, day before yesterday. A lawyer in LA who filed a brief using totally fabricated, hallucinated case citations, witness quotes, all this stuff. Terrible. So the judge said, "You're a bad person, $10,000 to you." Okay. Now, the reason I'm bringing this up is this is not the first time this has happened. In fact, this happened 6 months ago with a lawyer for Morgan & Morgan. It happened a year ago in Canada. I can go on in this direction. So, a word to the wise, when you use AI systems to write your text, to write your prose, to write your case filings, double check it, maybe triple check it, because this is a huge problem. So, over to you, Peter.
Okay, more news of the day. And this is about why AI chatbots can't process Persian social etiquette. And so the problem is here, you build one chatbot that's supposed to work for the whole world, and then it doesn't always work for all cultures. And so the problem they outline here is you go to Persia, you take a taxi ride, and the taxi driver says, "Oh no, my friend, that's okay. You don't have to pay." And what you're supposed to do is say, "No, I insist, I will pay." And then that's supposed to go back and forth 2 or 3 times, and then finally you pay and everybody's happy. But with the chatbots, which are like doing translations, say, "Oh, isn't this awesome? You don't have to pay." And then they get up and leave, and the taxi driver says, "What's wrong with that person? They screwed up. They don't know the way it's supposed to go." Right? And so this is a problem, that we build these systems that we think are general and work everywhere, and they don't work everywhere. So that was one from yesterday. Here's another one. So this is personal for me. This is Bob Ansler, passed away. I just heard about it yesterday. So I knew him when I was a grad student. He was already sort of a senior person. And so I want to talk about this for 2 reasons. One is, it's just amazing that this entire field only spans basically 1 generation, 1 lifetime. It's like, you know, if I was a physics student and I said, "Oh yeah, I met Aristotle, and then I met Newton, and then I met Einstein, and then I met Hawking, and you know, we all know each other," right? That's the case of what it is in AI. Now, what Bob did is, I think he should count as the first person to build a large language model, although it was a lot smaller. And so what he did, right, so he came up at a time in which everybody was just sort of doing things by hand. They weren't looking at any data. And he said, "I think there's a lot of data in this pocket dictionary, right? All these definitions of words and so on. I want to process that by computer." At the time, Merriam-Webster didn't have computers. Their dictionary was on a typesetting machine, and the input and output to that machine was these paper tapes. So he got them to send him a box of paper tapes, and he figured out what they meant, and then he sort of built a model of the definitions of all the words. And that was one of the first uses of that kind of data. And one of the conclusions was, yeah, you can get something useful out of that, but out of a 500-page dictionary of what it is, you can only go so far. And I think what nobody quite realized at the time is, they said, yeah, data will only take you so far. Now we have to really understand what's going on inside the head. What they didn't realize was 500 pages or 1,000 pages or 10,000 pages will only take you so far. But when you have billions of pages, everything changes. And that's what we've seen over the last 5 years. Okay, so back to the continuation of the lecture. And what I said is, we've got some training set. We've got some possible models to interpret that data. How do we decide which of those models is the right one? Well, one way you can do that is get another training set and then look at how they perform. And when you choose the data randomly from some process, you'll get a little bit different each time. And you can look at that and maybe understand what's going on, right? So first off is this polynomial model, like maybe that's overfitting, right? So there are what? 15 data points. If you have a 15-degree polynomial, it's guaranteed to be able to go exactly through every data point, but that doesn't mean that's the right model, right? So with one data set, there's a spike that goes up at the end, and with the other data set, there's a spike that goes down. It seems like it's missing what's really going on, and it's just kind of hallucinating results. So that's probably a bad model. On the other hand, over here, you say, well, maybe the linear model isn't capturing enough. With this sample of the data set, it looks okay. There's some error, but it's not too bad. Over here, it looks like maybe there's really some groups here, and it's missing that. And so, maybe something in the middle is just right. And so this is the way we figure out what's going on. We come up with models, they make predictions, and then we have to test out those predictions, right? Because the answer isn't in the data alone. The answer is in the real world, and we have to interpret that. Okay, so I want to very quickly go through just one example of how we go end to end to try to do machine learning. And this is one of the classic data sets. And we have some data about instances of these flowers, and the task is to say which variety of iris is each individual element. And so here's the data set, and it says the length and width of the petals and sepals, and the answer for what they are. And you try to come up with a prediction for that. And here's one way to do that, is this decision tree approach. You ask a question, what's the width? Is it more or less than 0.8? And if it's less, then we know for sure that's setosa. And if it's more, we have to figure that out. That's one possibility. Another possibility is this neural net model, where we just say we're going to feed in those numbers. There's some numbers in the middle that the system itself will optimize to be the best, and it will come up with a prediction. And then we also want to try to understand the data. And so we do things like data visualization, right? Because the results was either was a tree or it was a matrix of numbers. You can't really understand what's going on there. So we do these sort of visualization tricks of plotting one dimension against another. And then we can see things like, oh, it looks like the petal length does a good job of separating out the setosa class from the other two classes, but these two classes still overlap. So that's why you need to look at all the data all together. And this idea of visualization is really important in getting it right? Because you can get a number out that says, okay, I'm 95% accurate, but you don't have confidence that you've really done the right thing unless you understand what's going on. So visualization is a big part of that. I just want to talk a little bit more about how we've changed over the years. So this was an XKCD comic from 2014, and it's about how engineers have an idea of what's hard or not hard, and product managers often don't, right? So the product manager says, when the user takes a photo, check whether they're in a national park, and the engineer says, yeah, give me a few hours, I'll code that up. And then they say, and then check whether the photo is a bird, and they say, well, I need a research team in 5 years. And the product manager didn't know which one of those was going to be harder. But in 2021, this guy came up and solved that problem. And he says 60 seconds. The video is actually 1 minute and 8 seconds. And he did speed up a little bit in the middle. So I think it was probably more like 5 minutes. But going from 5 years to 5 minutes, that's a big jump in 7 years. And we can do that now. Okay, so let's do it. All right, enough of me showing you stuff. Let's actually build an AI model. And so type in that URL or scan that code and press the Get Started button. And let's do this in groups of 2 or 3. It's easier because it's more fun to sort of work with a partner. So group together with your neighbor and do that.
It's also probably easier on a laptop.
Yeah. Yeah. So find somebody sitting next to you who has a laptop and get started. So press that get started button, and you should see something like this. Okay. I just wanted to interrupt for a second because some of you are going great and are already started. Some were a little bit confused by the interface. So I just want to say one simple approach is say, let's do an image model, then let's do webcam, and then it says hold to record. So I'm going to build something that distinguishes between a fist and open hand. And then I say train the model, and then I'll preview it, and I'll show a closed and an open hand and see if it gets it right. So something like that, but you should do what you want to do, but I just wanted to show sort of basically how that works.
Okay, everybody, how did it work? Okay, anybody have trouble? What happened with your?
So Wes and I, we originally just did like we're trying to classify our faces, and it worked really well. But then Wes had the idea of like including like just a blue background over us. And when we did that, it turned out like it was just classifying the background and not our faces. So like when he zoomed really fast, it would say it was me.
Yeah.
And so yeah, I guess that was the problem with it. Yes.
So I broke several of them by standing in the background.
Yeah. And since we're have a high dynamic contrast, we can screw up all kinds of things. Somebody was doing thumbs up, thumbs down. Was it you guys? How did it work?
It was fine with thumbs up, but
Yeah.
then with thumbs down, if you saw like my nail polish, you wouldn't be able to classify it.
Oh, yes.
And I think for you, it just didn't work at all.
What can I say? This is exactly part of the point of this class, is the conditions under which these things succeed and fail. Anybody else over here have interesting results? How'd you guys do? How did it go for you? What were you doing? You were doing interesting dance moves.
Yeah, we're in the dab, we're in the woe. Keep motions is great. And then now it's actually doing pretty good. So if you give it a bird, like a middle finger, that's about it. I don't think that's acceptable. So pretty good.
Yep. So I'm waiting for my emails. We'll look at the images later, but this team over here, the Hawaiian Aloha Shirts classifying team, how did it work out? Well, you have to say what the classification was.
What's classy versus what's tacky. It'd be really cool on my writing website to have this model where you can, it'll tell you if what you're wearing is classy. And I take the result for the
We're sorry, Peter.
That's the fun movement, denoted as tacky.
But I do think that's a really nice app to put on your website. To do. So this is basically a classifier. I saw a few people using images. The rocket ship people. Where were you? That was it. How'd it work out?
Rocket images classified them to be real rockets and like fake model rockets. What was interesting is we had ChatGPT make a realistic rocket, but get rid of the background and make it white. And when we put in the one with just a regular background, like kind of blue in the sky, I thought it was a real rocket. So we got rid of the background. And thought it was real.
Okay, so this is a background issue like this. So a big problem with a lot of these classifiers is you don't know what the signal is. I don't think we know in the Aloha classy versus non-tacky shirts what constitutes tackiness. Maybe it's the presence of a white beard. In any case, this is one of the. I love this example because people find such interesting cases. There was one team last year who had playing cards, and they built like a six-way classifier for different playing cards, because that person happened to have them in their backpack. Okay, great. Thank you for that. Let's go on to the next segment, which is my lecture. Oh, wait, before we do that, I want to show you this. This is our syllabus, which you should all know and love by now, right? The thing I want to point out about the syllabus is it now has the CA office hours and contact information for them. And with each class, we put up the video of the class. So this is the link to the YouTube video with a really profound pose on it. There's also an outline document, which gives you the sort of summary of the whole class. And there's a notebook. Okay, now, is it here? It's there, great. So there's now a notebook for this lecture, which will combine both Peter's part and my part. So you can go, I encourage you to go explore what you can do with that, because we'll talk about the notebook in some detail in a few weeks, okay? Just want to make that, and there's the readings. So if you can't get to the readings, but I really would love it if you would read the readings, or at least skim the readings, right? Also, you can ask Notebook LM for a summary of that reading, because some of these are actually quite long. We say, for example, here, read the top takeaways of this index report. Oh, I forgot to update that. There's an index report for this year. Yeah, I'll fix that. Don't read it yet. Read it later this afternoon. But just read like the first couple pages, that's good, okay? I also want to point out that there's an extra special event happening this Friday. So tomorrow, right? Bjorn Hartman from Berkeley is talking about HCI systems in the age of code creation. So if you're all interested in vibe coding, and we're going to go into more detail on that, you probably want to come hear his talk tomorrow at 11:30. So it should be interesting. He's a good speaker, and I highly recommend it. Okay. Did that? Now let's start with this. Video, oh, that's fine. So where we are at now, Peter just kind of gave you the inside story, basic ML, basic models, basic data. The next couple of lectures, Peter's going to be away next week, and so I get to tell you everything I know about AI and psychology. So how do people think about AI systems? What's going on with that? What are the failures? What are the problems people have with this? So we'll talk about this. We'll focus on Tuesday next week about designing AI, knowing what we know about people. And we'll talk in detail about mental models, which I will introduce today. So that's our plan for the next few lectures. So here are the key ideas. The key ideas I want you to walk away with are, when we design AI systems, we don't just take an LLM out of the box and we're done. You have to think about designing it, and we'll talk about what that entails. We are going to talk about user models and designer models and system models. And it's three different kinds of models. Okay, we'll talk about that in detail. And we'll talk about how these models get used in practice in AI systems. That's today, and maybe part of Tuesday. Okay? When I say mental models, in this class, I mean how the person, you or your user, thinks about what the machine is doing, right? This is one thing. We're going to talk in detail about this. But first, I want you to do something for me once I figure out my backpack is. Hey, Tobias and Adrian, can you help me I got a piece of paper. And we're going to draw your mental model. What I want you to do is to think about Google search, which is a classic AI system. Okay? How does Google search work? Okay, I'm only going to give you like a minute to do this. So once you've got the piece of paper, sketch out what you think the big components of Google search are, how they're connected, and where the human enters into it. Okay? Go. I'll give you like a minute to do that, and then I want you to turn to your neighbor and explain what you drew and why, okay? So what did you discover? Anybody comment on their model or their neighbor's model? Who has a brilliant model? Who has no idea how things work? Yeah.
Well, I think I have a model that would have been the case years ago, where there was a search and then you get matches for combos of the words, diagrams, or whatever it is. And there's like 1 billion or 2 billion of those. And then the most common of those go to the top. And that's
Got it.
kind of, I think, at a basic level, probably how it works.
Right, right. Anybody else? Well, how many people agree with him first? Okay, we're going to say half, okay? And what did you have?
Yeah. The group here, I mean, also, like, who's doing the search matters, the search engine optimization matters, the geography of where you are matters. And there's probably some algorithm, rather than just brute force, there's probably some algorithm to look at where you're more likely, given that combination of words, to find things. Right? So there's probably something.
Okay, Rick, anybody have another version of the model? So let me tell you, I have asked this question a lot. I have a stack of paper about this high at home, which is collected from classes like this. I have over 1,000 examples of people's mental models as drawn out on a piece of paper. And this is a very common one, something like that. There's a query, there's a front end, and there's a Google thing that happens, and there's indices, and maybe there's diagram analysis, and a lot of the things I got back look a little bit like that. Here's the killer insight. That right there. Right? Magic happens. What that means to me is, I don't have any idea. Something magical happens. And so this class is interesting because about 1/3 of all of the pictures I've gotten over the years have a word like magic or something mysterious or something like that, something uncategorizable, undescribable, something magical happens. So this class is, how do people think about these things? Because if you have a magic component to your mental model, you've punted, you've given up, you have no idea what's going on. So Arthur C. Clarke, one of the famous science fiction authors past century, wrote that any sufficiently advanced technology is indistinguishable from magic. There's a lot about that that's worth thinking about. And I will then give you the contrapositive, Dan's contrapositive, which is any technology distinguishable from magic is insufficiently advanced. That's the definition of boring. So what we're going to do is try to thread this needle. And I want to point out that lest you think that you are above magical stories, I got this a little while ago when I got this thing saying I needed to install a new version of the Mac OS and the restart is required. Okay? Mac OS High Sierra supplemental update fixes an issue where certain character sequences could cause apps to crash. Right? I don't know what it's going to do. What part of the OS is it going to fix? It's just magical behavior. Now, you don't have a deep model for absolutely everything in the world. This is part of what you learn in university, is you can only learn certain pieces of the world, and the rest of it you just take as read. But I still have no idea why I needed to upgrade or what keystrokes would actually cause my OS to crash. I want to avoid those just in case. And so Google's done this too. This is a Gmail I got. And it's worth noting right about here, I've been sending this email and it says, oh, I've classified this as important according to Google Magic. Google is saying it's magical. I'm not sure I like that. Because there's black magic and there's white magic and there's indeterminate magic and there's complicated layers of this, right? So let's talk about conceptual models. So mental models, like I said, are the way the person, the human, thinks about the device, the system, the AI. Okay? And in particular, there's the designer conceptual model, which is the way the designer thinks this thing that they're building and designing is going to work. Right? So when you design a product at your next company, you will think, oh, I'm doing this, and it will be obvious. Right? Let me tell you the most important thing to take from today. There is no good intuition about design. You may think you have a perfect intuition about how your user population will react to your brilliant design. And most of the time you will be wrong, unless you've really spent a lot of effort trying to understand the user population, which a lot of people do not do. And in particular, when you're working with something like AI, which is very complicated behaviors, non-deterministic behaviors, trying to understand how the designer is thinking about this thing they're crafting is complicated. By contrast, the designer, the engineering staff have a model, conceptual model. Then there's the user. I'm the user, right? I'm trying to use this damn thing that the designer's made. And it's got stuff, and I've got years of experience with this thing. Say, consider your favorite text editor. You've got a lot of practice with it, right? Now, you probably have noticed over time, the spell corrector has gotten better and better and better. It now corrects things that it would have left alone before. So the product itself is evolving underneath you. That's part of my mental model. It's the way I think about it. And these mental models are created through the experience people have with the system. So the key point to keep in mind here is that the designer's model, the designer's mental model, may not be the same as the user's mental model. In fact, it's almost certainly not. Your chore, your task as a PM, as a designer, is to try to build those, make those align as much as possible. It's also worth noticing that mental models are usually incomplete. They're often inaccurate. And people hate to update them. And so what you are trying to do is to build a system, an AI system, where people will very quickly acquire a mental model that is accurate and predictive and does all kinds of good stuff for them. But you don't get a lot of shots. You only get a few shots to build, to craft a mental model that people understand. So I want to show you a short video that captures this conundrum in a beautiful way. If you've seen this, just bear with me. The people who haven't seen it, you'll see what I mean exactly. They've overlearned. So this is funny. Why? Because obviously the user doesn't understand what the designer understands. Designers gone to a lot of trouble to make sure that the shapes are reflected in the whole pattern on top. And the user doesn't pick up on that. But they have found a perfectly working solution. In fact, you can argue the user in this case has found a solution that's better than the designer. I used to run a big human factors lab at Apple, and we had one of those classic laboratory rooms where you have half mirrored glass on one side, and you have the user sitting over there with a computer, and on the other side of the glass, people would come in and watch the experiments as the subject was doing tasks using the latest software. We would bring people in, and every so often, we would bring in the software engineers that had built the system. Come in, let's watch people using, and this would happen. Almost exactly that. And my job, as the person who ran the lab, was to basically prevent the engineers from pounding on the glass and shouting at the user. Quick, to the upper right, dummy. No. You think you know what the user is going to do, but they will often take the path of least resistance. And that's what we're seeing here. Okay, advance to the next slide. There we go. Now, everybody lives in a place that's got some kind of thermostat, some kind of device that senses the temperature and changes the air conditioning or the heating to do whatever to get to the temperature that you like. Or at least they mostly do this. Sometimes things are wrong, but whatever, right? So there are thermostats that are like this. This is a classic thermostat. The way it works, the mental model for this that you should have is a little strip of metal kind of coiled back there. You can barely see it there. And it changes shape according to the temperature. And then there's a little switch. You see this little bubble right at the very top, that little bead of mercury. And when the temperature gets to a particular location, that the coil uncoils, the bead of mercury then closes the switch and turns on the heater. Easy. So the temperature goes on, and then as the room heats up, it uncoils and it disconnects. It's a classic device. Okay? And so most people think the way a thermostat works is what's called the flow model. That is, it changes the amount of hot air coming into the room. And so when you take your thermostat and set it to 99 degrees, the room will heat up faster, right? How many of you believe this? How many of you have, right? Thank you for admitting it. If you set it to 99 degrees, it will heat up faster. Let me tell you, it's a binary device. It's on or off. It has no notion of fast or slow. Now, modern thermostats are somewhat different, but then you get devices like, like this one down here in the bottom right, which is a baseboard heater, which has a more sophisticated interaction model. But the mental model tells people how to use the device. That's what a mental model does. It tells you how to use the device. So your mental model determines all kinds of things. It determines what the normal appearance of the system is and how it acts. It tells you how to use the system and how to repair things when they go wrong, right? That's what a mental model is good for. So I have a mental model of this device. This is my thermostat in my house. And that's literally my finger changing the setting here. And this is a better thermostat. It's got a computer inside of it. It's got a computer inside of it, does all kinds of things. You can, using these buttons, set what time of day it goes on, goes off, blah, 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 blah. Set the temperature range, high, low. It's a very sophisticated device. And you know it's sophisticated because right here, the thing that says reset. I have to reset my thermostat? Yes, you do. Because it's a computer and the software sometimes glitches. And the only way to fix this is to get a little paper clip and push the little micro switch inside the thermostat to fix it, to reset it. It just does a cold boot. Okay? Or you could do the other thing, which is, how do you fix anything that breaks? What's the first thing you do? Unplug it. You do a hard reset. Or you take out the batteries, right? We've all done this a million times because you can't debug it. So you cause a hard reset. In this case, they put the hard reset button as a handy paperclip switch. Thanks. Now I got to go find a paperclip. So we've got even better thermostats now. We have AI controlled thermostats. So this is the one from Nest, and it detects your patterns are coming and going and builds a model just the way you think. Great, this is awesome, right? Technology advances. And so now we have not a little button inside to reset the thermostat, but you got to do this in case things get broken. You press your thermostat ring to open the quick view menu. You then rotate it to select the gear icon. You then select the reset and press the reset. That's what reset on the Nest thermostat is. Awesome. Now, the very top, you see that sentence? It says when you restart it, your Nest learning thermostat will not lose any of your information settings if you restart it, similar to the computer mobile, right? But down here, it says resetting the network will remove all the network information from your thermostat. Which one is true? I don't know. They obviously didn't try to reconcile the top with the bottom of the page. They were clearly written by two different people, right? So what's your mental model? When you reset this thermostat, are you going to lose everything? So I will argue that when you have magical behaviors in the user experience of systems, it doesn't help. It's basically a punt for the company to say, we don't want to get into the details. It will spoil your pretty little head. Don't think about it too hard. We don't want to tell you anything useful. So then I saw this. So Copilot, as you probably know from Microsoft, is the AI hook for a lot of stuff. So in Bing, for example, you can go use Copilot, you can use Copilot for GitHub, blah, 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 all this stuff. Great. They recently announced the Copilot function in Excel. And in Microsoft Excel, you can go to a cell and say, equal Copilot left paren, and then you give a prompt, right paren. And I found this fascinating, that Microsoft felt compelled to tell us that Copilot uses AI and give incorrect responses. Very top. In particular, to ensure reliability and use it responsible, avoid using Copilot for numerical calculations. Wait a second. You're telling me I can write an Excel function that will give me wrong answers? Absolutely. Okay. So I give them credit for telling you that you should not use the Copilot function to actually do math. So yeah, the mathy functions in Excel, like, right? So if you wanted, and I love this line here, tasks with legal, regulatory, or compliance implications, don't do it. Don't do it. Okay? What they neglect to say is what it's really good for, right? So interesting. This just came out, and I found that just fascinating, sort of a way to let people know what's going on and to help to develop your mental model. So we all have voice assistants. Probably you've got one in your pocket with Siri. Your Android people, you've got the Google Assistant. And this is the home assistant for Google from a couple of years ago, the Google Voice Assistant. Little box like that, which they marketed and they sold as a smart speaker. So that's the mental frame they're giving you. This, my friend, is a smart speaker. You can talk to it. So what's your mental model of the voice assistant on the smart speaker? Can you, for example, say anything? When you interview people, they are completely bought into this illusion. This person said to me in an interview, I could say anything I want to it. It just understands me. Now, reality is it's not quite true, especially after they tried to send a text message and rephrase the command 3 different times. They could not get it to work. So what's your mental model of it? Interesting. This is the same person. Oh yeah, it understands anything. Okay. I must be saying it wrong. Here's an interesting thing about a lot of AI systems. When people find they don't do what they want to do, they assume that the error must be with them. It's self-blaming. And we see this in our studies all the time. I couldn't find the answer on Google. I must have said it wrong. So question for you, is the voice assistant guided by a grammar? What would be the implication of that? Well, I'll tell you, first off, most people have no idea what a grammar is. I would say 99.5% of people who use this device have no idea what a grammar is. And we just keep, Google keeps changing the recognition system. So it's difficult to create a mental model. Wait a second. This is radically different now than it was a few years ago. A few years ago, you would download, say, your favorite spreadsheet program, and it would be the same program for the next 10 years. Now, of course, everything runs off of cloud updates. In particular, these things have internal recognition packages and action packages that get pushed on a kind of almost daily basis. And so stuff that worked today doesn't work tomorrow. This is a problem for developing a mental model, partly because, remember what I said? People hate updating their mental models. They don't want to do it. And so mega corporation pushes a brilliant new AI system. Maybe they say, and it also does this, that's, and that, and the other thing. But people don't try it. And as a consequence, a lot of that work gets flushed. So, user models. Okay, we've been talking about mental models. Okay, that's mental models to here. User models are how the machine thinks of you. So somewhere inside that box, there's a piece of it labeled user model. So Dan uses his machine every morning at 5 a.m. to 7 a.m., blah, 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 whatever that representation is. So let me tell you a story. This is my very first semi-commercial AI product, which was when I was at Xerox PARC over there, just down the road. I was in 1982 working on building a help system for this printer copier, the infamous Xerox 8200. It's big, it prints very fast, it's great, but it is immensely complicated to use. And so the executives at Xerox said, hey, Russell, why don't you put some of the AI stuff on there to make it easier to use? And I was working with Richard Fikes at the time, and Richard and I said, yeah, we can do that. So we built a help system, which then the experience we had with it was so interesting. The experience was so interesting that Lucy Suchman wrote this, which is her PhD thesis, on the experience that we had developing this piece of code. I will spare you reading this entire book. It's really good. I do recommend it, actually. But basically, the upshot was people don't interact well with AI systems. That's the upshot. Like, oh man, how did we screw it up so badly? So I will tell you, what we had done was, this is, as Peter has said, we had come from the classic era of AI. And so we go back in the 80s when things were knowledge-based. And so this was a knowledge-based system. And you would describe, this is a representation of what the UI looks like. You would say, my goal is to do this, this, this. I want 24 copies, one-sided, two-sided, paper shifted, blah, 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 blah. You say all these things, right? And then you say create. What the system would do is create a plan. So give you this sequence of steps. And as you did it, it would put little check mark next. Great. What could possibly go wrong? Well, I will tell you, when people have to do these steps, for example, remove stock from paper tray 2. The first question they ask is, where's paper tray 2? And what is stock? So a big part of my job was to build the help system that would show you with interactive shaded graphics, 3D graphics, rotating things, where paper tray 2 is. I animated it opening up and blah, 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 all that stuff. Just what you think. But what we didn't account for was the way people would use those things. So the user model of this was pretty good. It was kind of impoverished. It didn't really know where you were or what you were doing. We had no location information. we had a great conceptual model, designer model was great, but the user model, not so great. This was the previous UI that we replaced. You can see why they asked for help, right? So the huge problem for the 8200 AI system that we built was we didn't know what the user was doing. So what they would say, the instruction would say, take the paper out of tray 2 and put the stock in place. We wouldn't know. Were they sleeping? Had they walked out of the room? Were they looking at the right place? It's over here, it's not over there. And so instructions would roll on the screen and we had no idea. And so we had a basic human factors problem. So building a user model relies on being able to sense what's going on in the world. So if you've got a self-driving car, it's full of sensors. And it's actively sensing the person inside the car, people wandering around outside, other cars, bicycles, babies walking on the street, everything. So sensing, that then builds up the user model. So our user model was inadequate for the task. We then had to take that data, the sensory data, and then interpret what people were doing. So the interpretation was not great either. When we try to build our models now, we have to do things like tracking language use. So we understand what terms people use, what concepts they have, and we try to create these explicit models of what they're trying to do. So we then differentiate our user models for individuals. So there's Lucy's model versus the class's model. Right? So if you're building something like, say, Google Search, you want both models. You want to know what Peter's doing and what terms he uses and what he's interested in versus the aggregation of everybody because they serve two different functions. So these models are deeply important. And this is another sort of throwback. This was a piece of work I did in 1988 where I built, which is basically a knowledge graph. So you've got these nodes which show how knowledge decomposes into constituent parts and in relationships between them. We then built an AI system on top of this, which would teach you how to use, in this case, this is part of a knowledge graph from how to use a multimeter, particular device. So we built this and it was great. And this is still a thing. This is now in Khan Academy. This is their model of the student. This is their user model, trying to represent what the student needs to know. And they track what the student has done. So when you use something like Duolingo or any educational system, they track what you're doing and they track to mastery. So what this is trying to do is say, oh yeah, I see that Bob knows how to add 2-digit numbers by marking tens. That's a skill. And part of what a good AI educational system does is they have this big knowledge graph in the background. They track what you're doing and they mark your level of skill at that. They also mark the things you've forgotten about. Because once you've learned it, it's not forever, right? Once upon a time, I knew how to take square roots manually. I no longer know that, right? And so people forget. And it's important to remember that people forget. Because if you're trying to build a user model that does not take into account forgetting, you will make incorrect inferences. You will conclude things that I believe you know that you don't actually know. So it keeps going on and on. So what could be missing? We've got knowledge, we've got behavior tracking, we've got all these pieces. Well, there's more. There's more to the situation. So current emotional state, somebody is yelling at their computer. You probably want to know that. We would like to have a history of this person beyond simple whether or not they can do this particular thing or not. And I'm going to say this multiple times during the class, understanding the user as a user, how sophisticated they are, what language they use, what concepts they have, what terms they understand. Give you an example. This is Google Maps. And what it does here, it popped up this thing saying, oh, Dan, you've got a reservation at Comfort Suites at UC Davis. You got that reservation. You need to check in today, so you should probably leave about now. But what it doesn't know, what the system does not know, is that I called and canceled yesterday. This is actually a fundamental problem with lots of AI systems, is keeping their state of the world up to date and accurate. Because I will often, as a human, do things that are outside of the system. I do not consult with ChatGPT to cancel a hotel in Davis. So it doesn't know. Right. A really good human assistant might overhear me calling and saying, oh, forget it, I can't make it tomorrow. Right? So the problem, this is in some sense called the frame problem. How do you know what in the frame of your knowledge has changed? And if I do that, if I cancel my trip out to Davis because I canceled the hotel, I probably don't need that Uber rental. I don't need that Uber reservation. That's the implication. So you get this cascading series of consequences from changing something in the world. Here's another example. So these are all examples of how the user model fails. Okay? User models break. One way is not by not tracking what's going on in the world. Another one is, this is the Google Calendar on my phone saying, you need to leave now because you need to get to Bodega Bay. It will take you 2 hours and 11 minutes to drive there. So Bodega Bay, if you don't know, it's a town up on the coast. It's about 2 hours away. Right? What the system did not understand is I reserved a seat at Bodega Bay, knowing Bodega Bay is the name of a conference room in Building 43. The computer didn't know that. The AI system does not have a distinguished model of how I'm using that term. So when I say hold a seat at term city name, what it should infer is I mean the name of a conference room in my building. What it's doing instead is saying, oh, you mean the city. No, I don't mean the city. Now, you can understand what the problem is here. For example, we also have conference rooms at Google called Larry Page. Yes, the Larry Page conference room. And so if you make a reservation to hold a seat in Larry Page, I don't want to think about what that could do, right? So you have to be able to make these kinds of inferences and keeping your user model and trying to help your mental model as we design these intelligent systems. This is not an intelligent UI, but this is a common trope you will see in automobile interfaces. Okay, raise your hand, don't say anything. Just raise your hand if you know what that triangle means. You know what that triangle means? Okay, wow. Smart class. Only a few people don't know what it means. Means that's where the charging port is, or the gas, in this case, gas. The gas cap is on the left side, not the right side. It's surprising how many people don't know that, because there's no explanation and there's no rollover state for that icon. You can't like poke it and hope to get a pop-up, right? It doesn't work. Or here's another good one where the customer comes in and says, I need 701 for my car. What went wrong here? I need 701 because the gas, this cap indicates that I need to pour 701 in there. Okay. Point is, UIs can go wrong in interesting, mysterious ways. UIs also, you should know this by now, won't be a surprise to you, I think, but UIs have a tendency to rewrite themselves as you use them. So for example, here's me editing the slide deck for this, and here's me trying to figure out where all these things went. So those are the same, right? These functions are the same from that and that. But what happened to that? Right? So in this case, we've got a new thing here. An old thing disappeared, and now we've got a new thing over here. So these are all UIs that are very contingent upon this, the width of the screen, contingent on what special state you're in and all that. I will tell you that if you ever sit in a customer helpline, this is the bane of your existence. The problem is things change. I mean, literally, if you change the width of the window of Microsoft Word, like by 1 pixel, all of a sudden the whole UI rewrites itself. You will get a completely different display. And a lot of people will say, where did my selection menu go? Make your windows smaller. What? Yeah, it depends. And there are UI people who design this and think, yeah, this is fabulous. Drives users crazy. So I want to tell you this important concept. For all UX design, and in particular for your AI systems, there's a notion of transfer. Transfer is when you take the learning from one system and use it in the context of another system. So here's Outlook. Maybe you have used this on your Stanford account. What happens when you hit tab? You're sitting here editing this message, blah, 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 and hit tab. What happens? Anybody, just shout it out. It goes down to what? Tell me, where does it go in here? You're writing a message, and I hit tab. Well, let me tell you, let me ask you. Thank you for volunteering. What do you think tab does in a UI? Yeah, it's the next element. Yeah, right, exactly. So in this case, what it does is actually goes to the send button, which is great. If you're in Google Mail and I hit tab here, what happens? It takes you to the send menu, right? It takes you here, you go tab, boom, enter, done, right? That's exactly what you expect. Now, suppose you're here, this little pop-up, your calendar shows up, and I hit tab, what happens? You know there's a trick question, right? I will tell you, it takes you to the question mark. Because if you look at the code, it's the next item in the UI element list when you're composing this dialog box. That's the next one on the list. Don't do that. If you have an opportunity to leverage skills from other domains and other tools, reuse that. So what the designer should have done in this case is make sure send was #1 in the next element list. This is called positive transfer. So if you have that game controller and you switch to another game using this controller, positive transfer means that the buttons are in more or less the same place, and green means green and red means red, A means A, B means B. So if it works consistently, that's positive transfer. And the thing you don't want is negative transfer. Negative transfer is when you go from system A to system B, you do the same thing in both contexts, and it does something different. So I want to share a photo by email, and I use system A. I can click on the right thing, do the right thing there. I do it on this one, and it does something different. That would be negative transfer. Now consider, so for example, I want to say using this system, play music by this person. I have years of practice using Google in my car. I say, hey, Google, play music by Google. I switch to the iPhone. The same sentence completely and utterly fails. Negative transfer. Imagine the consequences of negative transfer in your car. So in the US, the accelerator is on which side? Right. Brake is on the left. Now, as you know, you go to the United Kingdom, they drive on the other side of the road. Where's the accelerator? Yes? It's on the right. Thank God. Because when I went to the UK and I was driving on the road, I thought, I don't know where this is. Where's the brake? It's on the left. And of course, it means if they had switched them, which would make total sense if you're a UI designer. If you're a CAD designer and you're trying to lay out the design of the car, you copy paste rather than reflect, right? They're both pretty easy. You could argue you should have the accelerator on that side, but it would be terrible. Americans would die by the troves, right? So we don't want this. I'll give you one other example, and we're going to skip to the final question for today. Here's an example from, which one is this? This must be PowerPoint. So if you want to do an animation, what do? Right? You click on the animation tab. Now, suppose you're using Google Slides. Yes, comment. Yeah.
So in theory, how that pattern of the way to think rather than
Yep.
is that effective or is that just
So, yeah, basically as a marketing lock-in.
Yes.
Yeah. So that's the argument a lot of PMs will make to you. We want to lock people into this so they learn how to use it, and when they transfer to that other system, they have a terrible experience. However, it works to a limited extent. It also pisses a lot of people off. So do you want negative attribution or positive? So that's a great point, though. Let me finish off this one. So if you go here, what you have to do in Google Slides is search for the animation menu, except, wait. Here I am searching for animation. And I don't see the menu. Where's the menu? Everybody calls it animation, right? Wrong. It turns out in Google Slides, it's called motion. I don't know why. Terrible UI design. Negative transfer, right? The other negative transfer is on PowerPoint, the animation menu is always up there. It comes and goes on Google Slides, depending on how wide your window is, blah, 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 right? It's a terrible, terrible design. We don't want the same thing to happen in our AI systems, and we'll talk about that. Oh, wait, I got this one too. One more example. There's also, in addition to negative and positive transfer, category of errors called predictable errors. You know, for example, if we paste a match style on Apple, you can go Command Option Shift V, which I know everybody does. It will actually copy paste into a new document with the style attached, right? With the formatting. You can do that same thing with motion. That's great. Option Shift B. V, B, they're right next to each other on the keyboard, right? Here's another good one. So if you send an email, there's submit and cancel buttons right next to each other. A fair number of errors are caused by people clicking on the wrong one. Suppose this is a command for a login to a nuclear missile launch. Don't be that designer, okay? Last one. Control M, Command M are right next to each other. Control M in Google Slides creates a new slide. How lovely, a new slide. If you happen to slip and press Command M, it hides the entire thing. It makes it all go away. Good luck finding it. If you're like me and you've got 50 windows, one, that's not it, two, that's not it, three, that's, you know, it's a predictable error. Okay, so let me jump forward here. And we will jump back, we will return to this point on Tuesday. Okay, but this is your debrief for today.